Yes, here we are. It's the Physics 2A video lecture. Once again, Physics 2A video lecture 17. We're going to start off with announcements. This is actually going to be a short one because it's really just the review and heads up before the final exam. So first of all, I'll ask you to turn in any homework that you want to turn in by Friday this week. So the 8th of May at noon. This time at noon, because it's a lot, a lot of stuff comes in there. So turn in anything you have by Friday. I'm not actually giving a new homework assignment, but you may have something left over, okay? Good, what about the exams? The Tuesday and Thursday section has their exam Tuesday, May 12th at 5:45 p.m. So 5:45 to 7:45. I'll send out the exams a few minutes early, but I'll expect to get them back this time on the deadline by 7:45. So make sure you have all of your ducks lined up and make sure you're able to turn in a good, clear set of pictures. I'll say a little more about that. The Monday, Wednesday, Friday section has their exam Wednesday, May 13th, 8:45 to 10:45 a.m. Same thing holds here. I'll send them out a few minutes early. And then you want to make sure you have everything scanned, photographed, sent to me, by the deadline here. So that worked so well on the midterm. I'm pretty confident that we're going to be able to pull this off, get through this whole thing in good style. Make sure that you send your exam in by opening a new email message. Okay, don't attach it to the message I send out to you. That gets a little complicated on my side. Best for you to send in a new message with your exam on it. I'll write that down as well when I send out the exam. Yeah, so just the way we did it before, make sure you send me good pictures. The grading method that I have works very well also. If I can just have the exams in front of me on my screen and I write down my notes, and it works out well. Good, so more about that possibly later this week, and certainly on the day of the exam, you just get that email with the attachment and go to work on it. Okay, I was briefly reviewing the last lecture and I found a mistake right up there on the board. Didn't like to see that. There could be more of these. But this was at about the 6-minute mark. I had quickly written omega 2 pi L over M for the pendulum. I mixed things up. It's of course omega's 2 pi square root L over G. That's for the pendulum. The period of the another mistake here. This is the period of the pendulum. Okay. So I didn't actually belabor that anymore. I didn't belabor that anymore in that discussion because it had been from the previous lecture. Okay. So that's the period 2 pi root L over G. It's the important thing that the period goes with the square root of the length, right? We had talked about that at length in the previous lecture. So go ahead and make sure those corrections are there in your notes at least. Okay, these videos are unedited, one take. Okay, so this was wrong. There was our period. Okay, good. So that takes care. That's an important topic for the exam, of course, right? The period of the simple pendulum. So good. Let's send this up here and talk about what's going to be on the exam. And this is actually going to be fairly brief. I've mentioned before the 2 midterm exams. So that's 13 or 14 problems. I'm going to review the midterm exam, the second one. You want to know both of those exams really well. And if I wanted to, I could even repeat some of those problems with different numbers, or I could do problems that are very close to them. Okay. So first of all, the two midterm exams. The first one I had done completely in class back when we were meeting here in the lecture hall. This time I'm just going to mention what was going on in the second midterm exam. So for our second exam, what kind of problems did we have? The first one was the car that rolls down, collides, rolls back up the hill. Okay. So we could say we started at H and we ended up at H prime, and we wanted to know what that is. So the first part of this problem, you could just say V is equal to root 2GH. And of course you get that using conservation of energy, but it's a very standard result. Right, so car number one hits car number two that was at rest. So for the second part of the problem, you had M1 V1 equals M1 plus M2 V prime. Okay. And of course I had numbers in there, and I'm just giving you the outline of that. So now you had that V prime. Now with this V prime, you can use this same idea. The energy calculation will end up with H prime is equal to V prime squared over 2G. And you can express it in terms of the original H. So that was the way that problem went. Okay, conservation. This was energy, this was an inelastic collision, and this again was energy. And this is just like the ballistic pendulum problem. Okay, the second problem I really have to talk about a bit. So that's where we have a collision here, and then we go careening off in some direction. Perfectly inelastic collision in 2 dimensions. So you have to do the following. You have to add vectorially M1 plus M2 V prime. So you're adding vectors. And what happens is when I saw that people had not added as vectors, but just as the numbers, like 3 plus 4 is 7, then I immediately just gave 6 out of 10 points, okay? Because the point on this problem was linear momentum in 2 dimensions, vector addition. So that's why a lot of those problems ended up with just 6 out of 10 if they didn't get the vector addition right. Now, you remember that this turns into a triangle that you can label like this, M1, V1, M2, V2, M1 plus M2, V prime, and then take it from there. Okay. The other part of the problem was with the kinetic energies and the difference of those. Okay, I'm going to leave this board up here and just keep working down on this board right here. Okay. So, problems 1 and 2. Now let's look at what the third problem was. That was a near-Earth orbit problem. So that was Newton gravity, Newtonian gravity. And, you know, we had a central body, mass m, radius r. So to get the orbital speed, you know, we had g m r squared mv squared over r. That's the Newton's law of gravity, mass v squared over r. That comes from F equals ma centripetal. Okay. So to really do this one right, you want to cancel and you want to indicate what radius it is that you're talking about. So in this case, we can get v is equal to root gm over capital R. So there were a lot of lowercase r's there, but we want to pay attention to the difference there on the next go around. GM over R, and then as far as the energy, boosting it out to another orbit, that one gets interesting. For energy of any particular orbit, it's always 1/2 mv squared minus g m over r. So I could say that's energy for an orbit sub r, and the v can be related to this quantity here by this formula, or by this formula. So then the energy was, say, E sub 3r minus E sub r, and you have to carefully plug those in. And if you were boosting from a lower to a higher orbit, you were always going to end up with a positive value for this. So that type of problem as well. And again, to really get this problem right, you wanted to go from your lowercase r to the particular value of the radius of the orbit. Okay. So for example, if you have a central body radius r, capital R, and you're that distance above the surface, then the radius of your orbit is 2 times r. You're up another here, then it would be 3 times capital R though. Okay, so yeah, that's a heads up on how to do a problem like this. If you really want to get it right, you have to pay attention to those details. Yeah, then problem number 4 was also Newtonian gravity. First, the derivation of the escape speed. From the surface of a central body of mass capital M, radius r. So what's your escape speed if you want to launch and never come back? So then we have energy is equal to 1/2 mv squared over r. So there's our general expression. But if we're starting out on the surface here, then we have 1/2 mv squared minus gm m over capital R. Okay? And if we're ending up at infinity, and if we're coming to a stop when we're out there at infinity, then out at infinity we came to a stop, so v squared is 0 out there. And out at infinity, r going out to infinity makes this second expression vanish, right? The denominator goes to infinity, potential energy vanishes. So that's why it's a 0 out there, and m's lowercase m cancels, and we end up with v is root 2 gm over r. I'm not sure if I ever brought this up in class, and I just erased what I had on the board before, but this speed here is the square root of 2 times the near-Earth orbital speed. So the near-Earth orbital speed is roughly 8,000 meters per second, and the escape speed, this is v escape, is the square root of 2 times that, so 1.4 times that, it's 11,000 and some meters per second. So that's actually an interesting fact there. Square root of 2 times that near-Earth orbital speed. Okay, good. So this energy, and always remember for these things, you can always just label E sub A, E sub B, and work your way through. If you've labeled your point A, say here, and your point B, in this case, out at infinity. And if it's not out at infinity, then it is at whatever elevation it is. One heads up where people didn't quite always get this is if I said it was the distance above the surface of Earth was the Earth radius, then the distance to the center, which is the one that always counts, is 2 Earth radii. So be careful with that, okay? We're always referring Newton's law of gravity and Newton's potential energy, relating it to the center of attraction, which is the center of that spherical body. Okay, good. This was problem 4. This was 4. Let's see, what do we have for 5, 6, and 7? For 5, actually a lot of people got it. That was rotational kinematics. So a rotational kinematics could certainly be in the mix. Good. Rotational kinematics, you have to just have those formulas. So let me just say for that, you have to have those formulas available and in front of you when you're ready to tackle a problem like that. So formula sheets are a good idea to get ready for the exam, just so you have them all in front of you. So we had rotational kinematics. I'll just declare victory right there. What else did we have? Statics. Now the statics problem I gave, I practically promised you that one. I just think it's an important one, but if we do another statics problem, we're going to do a harder one. Okay, that one was very basic. So, we had that pin there, L sub 1, total length meter stick, and we had some mass here. And what I did was I had the meter stick at mass M, say, and then this mass here, 3 or 4 or 5 M, something like that. For my drawing, I'm going to use an M1 and an M2. So the meter stick has mass M1, we've got M1G, we've got M2, we've got M2G. And we were measuring the torque right here. So we had M2G L1, the other one, M1G, but the length is, the entire length of the stick is capital L. So this is L over 2. So this is L over 2 minus L1. So L over 2 minus L1 equals 0. And then you go ahead and solve. Okay, that was the exam problem. If we do another one on the exam, on the final exam, I'd have to choose one a little more challenging than that. And if you go back to our discussion notes and review for that exam, I had more challenging problems up on the board. So I'll just refer to those. Those would be in the other video lectures. And finally, buoyancy. And this is just one of my favorite problems. What did we have there? We had the ice cube that's tethered to the bottom because it's underwater and it would float otherwise. We wanted to find the tension here. So what we had was mass of ice, G. We had tension pulling down, and then we had a buoyancy force up. So I like to do these in steps. So if you have the net force equals 0, then you have the buoyancy force minus mass of ice, G, minus tension equals 0. Density of the surrounding fluid, water, volume, G, minus density of the ice times volume times G equals T in this case. And then you were just plugging the numbers in. Okay, so that's how that exam went. What about the final exam? So as I had stated earlier, the final exam, anything from the first 2 midterms is fair game, and so what I'll do is write down a short list of the ones that have come since then. And I'll also mention what wasn't on the midterm that could have been. So let's see here. So for the final once again, I'll write final exam. First of all, both midterm exams. Now, I already mentioned that our statics problem was pretty simple. We could put a more challenging one on the final. What else do we have there? Ah, yes. So in addition, a rotational dynamics problem. So you have your rotational kinematic formulas out there, and then of course you've got torque, you've got moment of inertia. So rotational dynamics problems and rolling, a rolling problem which we had stressed last time. I think I actually had those on the last review and we didn't actually get to them. So something of these types of problems could be on the exam. And ideal gas law now, the form of the ideal gas law that we're interested in, PV MK Boltzmann, temperature. We're interested in keeping the number of particles constant. The Boltzmann constant is a constant. So we get this kind of thing, P1 V1 over T1 equals P2 V2 over T2. In other words, that's the form that we can use the ideal gas law in. Temperatures, of course, in Kelvin. Temperatures in Kelvin. And the example that we had was the bubble that was rising to the surface and expanding. Down here at 1, it's a small bubble. Up here at 2, when it breaks the surface, it's a larger bubble. So the ideal gas law of that type of problem is fair calorimetry. Okay. So calorimetry, those problems, we're using Q equals MC delta T. Okay. But in a calorimetry problem, we're keeping a sum of Q's, Q sub 1, Q sub 2, etc. They all add up to 0 because the energy is just transferring from one object to another without any being lost. So then we have things like M1, C1, T minus T1 plus M2, C2, T minus T2 is equal to 0. So I'm not going to make it more complicated than that because that's just, conceptually it's the same if you could have 3, 4, 5 objects. It's just one equation, and there's your final temperature, which is common to both of our objects, and those are the initial temperatures. And if you do it this way, you don't even have to worry about which one is hotter than the other. They just sum up to 0, and then you've got one unknown that you can solve for. Okay. So calorimetry of this type, and then there's also the latent heat of fusion. I won't bother you with the latent heat of vaporization, so we'll be talking about melting ice, that type of thing. And, I'm not quite sure about the calculator policy. Everybody's at home with a calculator. If I make up really easy numbers, then you don't need a calculator. If I just say, go ahead and use the actual numbers, then we can use calculators to get the answers. So what I'll do is when I post the exam, I'll give instructions as to whether or not you need a calculator. Anything pertaining to that. It allows us to expand the class of problems that we have to solve, and the homework problems have all been able to use a calculator. So here also latent heat of fusion, so where you have to use, in your sum of energies, you also have to use Q equals M latent heat of fusion. That's for when things melt or solidify. And we had a few of those as well. Nothing that we have on the exam is going to be difficult compared to the homework. So, but yeah, that's a class of problems that was definitely a contender. And only a few more things here. Heat engines is on my list. So let's erase here. Now for the heat engines, we had a number of problems. And for the heat engines, you need to know the schematic diagram because it's just a good orientation. Okay? The schematic diagram where you've got the high temperature reservoir, the engine kicking out work, low temperature reservoir, etc. Okay, so you understand that schematic, and the formulas that go with it are the following. We have for an ideal QH equals W plus QC, that's just energy conservation. We have the definition of efficiency, regardless of whether it's an ideal engine or not, that's our fundamental definition of efficiency. But then we have the ideal efficiency, and we have the Carnot efficiency. This last one, very important to understand. The Carnot efficiency, 1 minus TC over TH Kelvin, okay? So you have to convert to Kelvin. It's fair for me to go ahead and give you temperatures in Celsius, and you have to add the 273, or I could just give it to you in Kelvin too. Okay, so that's a trivial conversion. So temperatures in Kelvin, and this along with the power formula, power work per time, and I'll also say energy or power work is power times time. This little collection allows you to solve any of these elementary heat engine problems, okay? Hugely important, actually. The heat engine, it just boils down to that, but it's such an important topic. And we had a decent little treatment of it, so that's okay. And after this, I'm just going to say a couple things about oscillations and waves. So for oscillations, and we had a good lab on that, for oscillations, you need Hooke's law, minus Kx. You need to know the potential energy of the spring, 1/2 Kx squared. And now this would be a time for allowing you to use calculators. Then you have the frequency square root of K over M, and the period 2 pi square root M over K. So we did a lab on that, and this in particular is for the harmonic oscillations that are sinusoidal. They have the cosine or the sine function describing their positions. Good, so you want this one. The pendulum, where I started with that erroneous discussion there. The pendulum, we're primarily interested in that result. 2 pi root L over G. It's really an important result for timepieces. It's an important result for verifications of the value of G. So very important. And the theory behind it, we'll say, was covered right here. So for the pendulum, we just cut to the chase, and we have that formula right there. Okay, finally, what about waves? Waves were the last thing we did. We had some nice homework problems on it, so I'll say a little bit about the waves. So first of all, we have lambda f equals v. Very generally, for a wave, And if you have a sinusoidal wave, goes like that, you have to be able to recognize what is the wavelength. There's the wavelength, okay. Then, for waves on a string, tension divided by mu. Okay. Again, I deliberately gave a number of problems here. That's tension. Okay. Make sure that's a little clear. Tension divided by mu. Because you have to a little time getting used to that. Remember, that was kilograms per meter, or mass per length of the string. And there's the tension on the string. So you could have some contraption. In our lab that we did not do had exactly this. We had an oscillator and we run strings over the edge. We hang a weight there. We were getting standing wave patterns. So a standing wave pattern would look like this. And what happens is the string is vibrating like that under the appropriate tension, and this is a node here. And the string's vibrating like that, so there's a blur. There's a blur here because the string's going up and down. So this, if you have a picture like this, this actually corresponds to one wavelength. And if this device is oscillating at a certain frequency, frequency times wavelength is the wave speed, and then if you had a mass here, you could even say, okay, what is the tension? So that's the type of problem here. Do not mix up this mass with the mass per length having to do with the string. It's completely different. As in all these labs that we did this semester, we're always hanging something off the end just to produce a certain controlled amount of tension. Okay, good. I think that's going to be about it. Let's see if we want to wrap this up somehow. In terms of the exam, once again, you've got the times for the exam. Got our correction there in the video lecture. We have our 2 midterms plus this set of 6-7 problems that you want to be confident about doing. The midterm exams went very well, so I'm confident that you guys are going to be able to do well on the final too. A little more of a time constraint this time because we want to turn it in on time, okay? And okay, anything else I have to tell you guys, I'll do that via email. And so I'm just going to wish you good luck on this final exam and on all the rest of your final exams as well. Good, so see you next time.